Chapter 31 is going to tell us all about electromagnetic induction. And the basic idea here is going to be that a change in our magnetic field, also known as a B field, induces an electric field. So if I have a changing magnetic field, also known as some kind of magnetic flux, then that changing B field, that magnetic flux, creates an electric field. We call it inducing an electric field. That induced electric field is then going to induce a potential, an EMF, inside of a circuit. And the real punchline of all of this is that the changing B field change in magnetic field is going to give an EMF into a circuit. It's going to move some potential into and through a circuit. And this concept right here governs almost all of our electricity. Our electricity is created through this process that we call electromagnetic induction. The entire topic of this chapter. Now there are a few ways that I can set up a changing magnetic field, and one of the first ways that we're going to talk about is something called motional EMF. And in this approach, we set up a circuit inside of a constant magnetic field. So we can hold the magnitude of this magnetic field, our B field, can be constant. It doesn't have to change. And the way I'm drawing this here, these little X marks, if you recall, they mean the magnetic field is going into the page. And what I'm going to do is I'm going to take a little piece of wire and I'm going to put it inside of this magnetic field. And what I'll need to do, I'll need to extend this magnetic field out just a little bit more so that I can take this wire and I can hook it up to form a complete circuit. Now I'm not hooking up this wire to a battery. There's no batteries in this little drawing. All I have is this little loop of wire inside of my magnetic field. And I'm going to specify that the length of this wire, the vertical length, is going to be a length L. So that's how tall this wire is. That's how much of this wire is in the magnetic field in the vertical direction. Now what I want to do is I want to drag this wire through this magnetic field. I'm going to give it some velocity. I'm going to pull it to the left. And I'm going to pull it to the left with some velocity v. I'm going to perform the right-hand rule and figure out what kind of magnetic force is going on here. I have charges, I have electrons inside of this little wire, and those charges are all moving at a velocity v to the left. I can use the right-hand rule and use my fingers to point in the direction of v, curl them down in the direction of b, and I find a magnetic force that's going to be acting down. But the right-hand rule gives us the force that would act on a positive charges, and I have negative charges inside of this wire, so the actual force that's going to be acting on these, the magnetic force on the electrons, is going to be acting up. Again, that's the right-hand rule. The right-hand rule gives us a magnetic force going down on positive charges. We have electrons in our wire, so we flip the direction that comes from the right-hand rule to get a magnetic force acting up. So if my magnetic force is going up, that's going to set up a nice little electric field. This induced electric field is going to set itself up inside this wire, and this is going to set up in the same direction as our electric force, because we know the definition of electric field. We know force is equal to charge times electric field. So my electric field is going to set up inside of this wire, so I have a little bit of positive charges down towards the bottom, a little bit of negative charges up towards the top. That's going to be an induced electric field. inside of this wire. And because of this force that's induced by this motion V that induces this electric field, my charges are going to start flowing. Any electrons are going to be repelled from the negative side of my electric field that we have up top. So electrons are going to move away, and they're going to flow through this circuit to move towards the positive side of that field, because opposites attract. So I have electrons that are going to be flowing. The electrons are going to flow around this circuit without any battery having been connected. So in a sense, this moving rod is pumping the charges. The rod is moving at a velocity v, so we can calculate the actual force that this rod, that this wire experiences inside of our magnetic field. The force of something in a magnetic field is equal to the charge times the velocity you move times the field itself. And this is going to be equal to the charge times the electric field. That's the induced electrical force. So I can set these two equal to each other. These are the same forces. The magnetic force that's induced is the same as the force that actually induces my electric field. So I can get that Q times E is equal to Q times V times B. My Q's will cancel, and I find out that E is equal to V times B. But we can also take this a step farther. We can look at the electric field that I've set up. The electric field that I set up. If I multiply that by the distance that my electric field is operating over, the electric field is operating over the length of this wire. So that's going to be L. So E times L is going to give me the induced EMF. We get this from remembering that voltage, V, potential, is equal to E, electric field, times the distance along which that electric field acts. It's exactly what we have here. Our induced potential is equal to the electric field that's induced times the distance over which it's actually induced. And I can plug these values in. I can solve this wonderful little equation for E to find that E is equal to an induced EMF divided by the length of the wire. So I'm going to plug this in now into my electric field and find induced EMF divided by the length of the wire, the distance over which that electric field acts, is equal to V times B. I'm going to solve this for E. My induced potential is equal to L times V times B. To finally get my induced EMF from a wire that's moving inside of a magnetic field. Induced EMF E is equal to the length of the wire in that field times the velocity that it moves at times the magnetic field. I like to remember this as the induced EMF is lovable. And this equation for induced EMF equal to L times V times B is going to lead us to something called Faraday's law. So we can kind of rebrand this LVB for induced EMF in terms of something called magnetic flux. So magnetic flux, similar to electric flux, except we're going to attach a little b to it, is equal to the integral of b dot dA. This should remind us, look a little bit similar to Gauss's law, which some of you love and some of you hate. But that's really what this is. It's Gauss's law restated for magnetic fields. So this first term, this uppercase omega sub b, stands for magnetic flux. And the magnetic flux is similar to the electric flux. It tells you the number of magnetic field lines that pass through a surface. And we can see that right there in the definition for it. And we saw this the same way in Gauss's law. The magnetic field lines represented by B, and the amount that passed through a surface represented by the integral over dA, the surface area. So we'll kind of work with this and get rid of the integral sign by taking the derivative of both sides. So the derivative of the flux for magnetic flux is equal to B times dA, where by taking the derivative of both sides, I got rid of that integral that we had in there. Now our situation will draw again. We have this magnetic field, a constant magnetic field. And we have this little bar that's moving in that magnetic field. This little piece of wire, if you will. I'm going to flip the direction just a little bit, and I'm going to have this wire in my field, and I'm going to be pulling it to the right this time. Same concept, same idea, I'm just pulling it to the right. So at some later time, our little piece of wire is going to have moved. And again, we'll keep that same length L. Now what I need to do is I need to figure out what the magnetic field is here, B, and the area of my wire that's been inside of that magnetic field. I need to figure out dA. So to figure out dA, I know what L is. L is the height. Now I need to know the width that this has traveled. So I need to know, what is this distance? Well, that distance is the velocity times the change in time, times how long it took my little wire to be dragged that distance at its future time. So this is from Physics 1. We should remember that a velocity is given in meters per second, and we can multiply that by a time. Time is in seconds to give me meters. So this v dt gives me a distance. I just did a dimensional analysis to make sure that this was correct. So now I know that my dA, the amount of area that this little piece of wire has swept out, is equal to the length times the width, the height times the width. However you want to think about it, the height of L, how tall the wire is, times the width of the wire, v dt. Okay, so I can use all of this and plug it in to the definition of my magnetic flux that I got from before. So I get d phi for the magnetic field is equal to B, the magnitude of my magnetic field, times L times V times dt. Let's get all of my derivatives on the same side, so I'll divide both sides of this by dt. Just doing a little bit of algebra here to find d phi dt, the derivative of my magnetic flux, is equal to L times V times B. Exactly what I expected. Because of something called Faraday's law, which tells us that negative d phi dt, this magnetic flux, is equal to the EMF. So this phrase right here, the induced EMF, is equal to the negative change in the magnetic flux, is what's known as Faraday's law. one of the most puzzling parts of this is where this little negative sign comes in. And this comes from something called Lenz's law. So just for clarity's sake, we'll restate Faraday's law. Faraday's law, which we got by kind of deriving it from considering Gauss's law for magnetic fields. We get to Faraday's law, which tells us that an induced EMF, the induced voltage in a circuit, is equal to the negative change in the magnetic flux. Because that's all the derivative really is. It's just a change in a quantity. And this negative is quite perplexing sometimes. And that negative comes from the physical direction from the induction process. And as I just mentioned, this comes from something known as Lenz's law. And Lenz's law tells us that any induced current will oppose the change in flux that creates it. You see, nature doesn't like change. So it wants to keep the same amount of flux constantly going through it, so any induced current will oppose any change in flux that creates it. To get a handle on this, you'll really need to study up and look at a few examples. I recommend looking in your book at examples number 3, 4, 5, and 6. And one of these example problems will appear on a quiz. And also, check up number 31.3, questions 1, 2, and 3. That should be a big help in you learning and applying Lenz's law. The final part of this chapter that I'd like us to go over is about inductance, and in particular mutual and self-inductance. So let's say that I have two coils of wire. Coil number 1 and coil number 2. I'm going to say that coil number 1 has an alternating current. Also known as AC current. If I have an AC current, that means the current flips direction. It goes from positive to negative. It's not like the direct currents that we studied primarily in earlier chapters. So if I have AC current, that means the current I is changing. If the current changes, then that means the B field changes. And if the B field changes, that means that the flux changes. So if flux changes, we have induced EMF. And that induced EMF is going to be induced into coil number 2. So I could run absolutely nothing through coil number 2. I could have nothing going on over here. And just by being in the presence of coil number 1 that has some AC circuit, that has some AC current going in some direction through this coil, that's going to induce an EMF into coil number 2. And I can calculate what that induced current is. I can calculate that induced EMF. The induced EMF, E2, is going to be equal to the negative change in the flux through coil number 1. And we calculate this change by taking the derivatives. And a shortcut for getting these induced currents is going to come if we know the mutual inductance in our system. The mutual inductance we define as the letter M times di, the change in current in the first coil, dt, where this M is called the mutual inductance. And it's going to come from the geometry of the coil itself. You'll need to read in your book to figure more about that. This mutual inductance M, it has units. The units of M are labeled as capital H, which stands for the Henry. And this mutual inductance process is used to change EMFs inside of circuits. It's used a lot in transformers. It has lots of practical application. So to get power into your house at the amount that you need to use this mutual inductance. Something else that we have to work with, in addition to this mutual inductance, coils inducing currents into other coils, is something called self-inductance. If I have a coil of wire and I have a current changing inside of this coil. Same situation we had last time on the last slide, so I have a changing current. This will induce a changing magnetic field. That changing magnetic field can induce a current in a different coil. But it's also going to induce its own magnetic field changing. So a changing current in a coil induces a changing magnetic flux in that same coil. And we can calculate this as well. The changing magnetic flux that we get inside of a coil of wire is going to be equal to this letter L times the current in that wire, where L is something called the self-inductance. We can do this algebraically. If the problem or application is simple, we can also do it with calculus if we're given, say, a changing induced voltage and induced EMF that's going to be equal to negative L, the self-inductance, times a changing current, di dt. You can read all about all these equations in your book, and you will need to for this chapter. And most importantly, you'll really want to practice to try to understand this negative sign. Where does this negative sign come from? How does Lenz's law work? And what does it mean that induced current resists change?